Welcome to this explainer. Today, I'm going to be playing the role of your senior engineer. Together, we're going to debug exactly how a computer works, zooming all the way down to the microscopic silicon at the very bottom, and then building it right back up to the pixelated screen at the top. If you've ever stared at your device and wondered what's literally happening under the hood, well, you're in exactly the right place. Let's get into it. To give us a really clear, focused target today, let's ask a deceptively simple question. How exactly does a video game store and update a digital wallet when your character finds, say, 8 new coins? I mean, it feels absolutely instantaneous to us, right? But to truly understand how this simple memory allocation and update works, we have to trace the operation all the way down to the bare metal. We need to look at the physical reality of what makes a computer actually think. So here is our debugging checklist for today. We're going to cover 1. Down to the bare metal. 2. Building the logic gates. 3. The architecture of memory. 4. Compilers and code execution. And finally, 5. Rendering the final output. Okay, starting with section 1, down to the bare metal. At the absolute lowest, microscopic level, digital information is really nothing more than the presence or absence of an electrical voltage. And to control this, modern processors are manufactured using this incredibly fascinating process called lithography. It literally translates to writing on stone, and it's essentially a layered manufacturing technique. You start with a solid block of silicon that's mixed or doped with specific elements to give it unique electrical properties, like a p-doped base. Then, through chemical deposition, we add super thin layers of materials. We coat it in a light-sensitive chemical called a photoresist, shine a light through a mask to expose really precise patterns, and then use chemicals or hot plasma to etch away all those exposed gaps. By repeating this layering and etching over and over, we literally sculpt microscopic structures right into the silicon. And by shrinking these patterns over the years, we've drastically increased transistor density. That density is the absolute key to boosting modern processing speeds while somehow keeping power efficiency high.
Now, what we're actually sculpting with all that lithography are millions and usually billions of microscopic switches called transistors. Specifically, modern computers use pairs of these called CMOS. Think of these transistors as tiny electronic gates. A high voltage, like maybe 3.3 or 5 volts, opens one path. That represents a binary 1, or true. A low voltage, basically 0 volts dropping to ground, opens a different path, representing a 0 or false. So when you add those 8 coins in your game, at the very bottom of your processor, it's really just tiny physical gates routing electrical voltages.
Moving on to section 2, building the logic gates. A single physical switch on its own, it doesn't really do much. But when you wire them together, they create logic. This brings us into the world of Boolean algebra. We can actually map these physical logic gates to relatable, everyday rules, kind of like friends trying to agree on a restaurant. For example, an AND gate, built from those CMOS transistors we just talked about, only outputs an electrical true signal if both its inputs are true. It's like Bob, he's only happy if the menu has pizza and noodles. An OR gate outputs true if at least one input is true. Then there's the XOR, or exclusive OR gate, which outputs true only if the inputs are different. Charlie wants pizza or noodles, but absolutely not both. And a NOT gate, it just flips the input to the exact opposite. This perfectly illustrates how physical, voltage-based circuitry evaluates true or false conditions. And here is where it gets really cool. By networking these exact gates together, we can perform complex binary math. Computers, as you know, only count in zeros and ones. So in binary, 1 plus 1 doesn't equal 2, it equals 10, meaning a 0 in the first column and you carry the 1 to the next column. To actually do this electrically, your computer routes the 2 inputs through an XOR gate to get the 0 and an AND gate to trigger that carry bit. By chaining these simple physical gates together, we can add, subtract, multiply, and divide. This is exactly, literally how the system calculates the math to add those 8 coins to your player's wallet. Let's look at section 3, the architecture of memory. Once we calculate that new coin total through our logic gates, well, we have to store it somewhere, right? Think of computer memory like a giant wall of postboxes in an apartment block. Every single byte of data needs its own unique binary address, so the processor can actually find it later. Now, older 32-bit architectures used a 32-bit number for these addresses. That meant they literally ran out of physical addresses at about 4 billion bytes, which is roughly 4 gigabytes of RAM. As programs and video games got way larger, we physically ran out of postboxes. That is exactly why modern computers transitioned to a 64-bit address limit. It gives us an unfathomably massive capacity for data, easily managing the tens of gigabytes of RAM you see in today's machines.
This whole postbox system is vital for a core concept of modern computing called the von Neumann architecture. In this design, the actual instructions telling the computer what to do, like an instruction to add numbers, live in the exact same memory space as the data itself, like your 8 coins. It's all mixed in together. The computer only knows the difference based on a very rigid clockwork order. The instruction byte always comes first, followed directly by the memory addresses of the data it needs to operate on. Because all these electrical signals have to physically travel through microscopic wires, from the memory postboxes into the processor's logic gates, it takes actual time. So, an oscillating crystal on your motherboard acts as a clock, ticking billions of times a second. Think of a 2 GHz processor, for instance. This clock strictly synchronizes data fetches. It absolutely guarantees that the electrical signals finish propagating through the addition gates before the next instruction is allowed to begin. In fact, and this is mind-blowing, processors are actually limited by the speed of light. If a processor chip was physically too large, the signals simply wouldn't reach the other side before the next clock tick. How crazy is that?
Which brings us to Section 4, Compilers and Code Execution. So how do humans actually interface with this incredibly rigid address-based hardware? We certainly aren't sitting there manually typing out billions of binary ones and zeros. Enter the compiler. A game developer writes high-level code, like C++, which is totally readable by humans. It says things like wallet equals wallet plus 8. The compiler's entire job is to translate that human-readable logic into the raw, bite-sized machine instructions that the von Neumann architecture demands. The compiler does the heavy lifting. It figures out exactly which memory postboxes to assign to the wallet, organizes the binary byte sequences, and sets up the precise jump instructions so the program can loop indefinitely without just crashing. Concurrently, your operating system is juggling all of this in the background. It doesn't just manage inputs and outputs, like translating your physical mouse click into a cell command. The OS actively manages memory and handles all your concurrent program tasks. It safely partitions out those memory postboxes, so your game, your web browser, and your music app can all run at the same time without accidentally overwriting each other's data. If you click that cell button, the OS safely coordinates jumping to the compiled logic we just translated entirely without disrupting anything else happening on your machine. And finally, Section 5, Rendering the Final Output. Now we just need to get those newly calculated coins to actually show up on your screen. To do this, we have to talk about pixels. A screen is really just a grid of microscopic LEDs grouped into red, green, and blue subpixels. Remember earlier how computers group information into 8-bit chunks called bytes? Well, the absolute maximum value you can store in an 8-bit binary sequence is exactly 255. Therefore, the computer sets the brightness of each red, green, and blue light on a precise scale from 0 to 255. By varying these 3 bytes, your eye is completely tricked into seeing millions of distinct colors. Drawing the game interface is really nothing more than running those fundamental logic gates through complex arithmetic algorithms. The processor calculates the shapes, colors, and coordinates, and then it overwrites the specific memory addresses that directly control the display's pixels. And it repeats this massive loop maybe 60 times a second to create fluid motion, finally displaying that shiny +8 in your coin interface. It is an incredible, almost unbelievable choreography of raw mathematics happening at blazing speeds. Everything we just debugged today proves a really beautiful reality about technology. Computing is all about building up simpler concepts to achieve more complicated ones. From chemically etching silicon to pairing true and false statements in logic gates to routing bytes through a 64-bit memory block, all the way up to painting millions of pixels, it is all just the layering of fundamental electrical truths. Thank you so much for joining me on this explainer. The very next time your character's coin wallet updates instantly on your screen, I really hope you can visualize the billions of transistors firing in perfect unison to make it happen. It really leaves you wondering, doesn't it? If vast, complex virtual worlds are built on literally nothing more than doped silicone and microscopic switches, what's seemingly impossible?
If you enjoyed this video and learned something new, like this video, comment your favorite programming language, subscribe to Future Break Coder, because many exciting coding and futuristic tech videos are coming soon.